A simple extension of a field is a bigger field that contains one additional element that wasn't in the field before, as well as whatever other additional elements must also be there in order to make that bigger set a field. So, in our last video, we began talking about simple extensions of the rational numbers. For example, how do we take the rationals and then tack on something like the cubed root of 2, which is not rational, and then build whatever other arithmetic that we need in order to make that bigger set into a field. What we get is the smallest field that extends the rationals and which contains the cubed root of 2, and we call that the simple extension q adjoin cubed root of 2. But it turns out that when we do a simple extension, we might not always get the same answer if I do it one way and you do it another way. In other words, simple extensions are not necessarily uniquely defined. And I'll be honest with you, when I first learned this stuff, this threw me for a loop. What do you mean there's no such thing as a single kind of simple extension? Well, in this video, we're going to take a look at a fairly basic example where we take the rationals and we extend them by the golden ratio, 1 plus radical 5 over 2, which is irrational. And we're going to look at two different ways to do that. How are they similar? And how are they, in some subtle ways, different? So there are two ways to introduce the rationals to the golden ratio, 1/2 times 1 plus radical 5. And here are two different ways. One way is to just take the number gamma, 1/2 times 1 plus radical 5, and throw it in there. In other words, use that as the element of your simple extension. This would be kind of the most obvious way to do it. Just straight ahead, throw in gamma and see what happens. But you might say, gamma is made up of a sum of two numbers, one of which is irrational, but the other of which is rational. So why can't we just adjoin the irrational part? Because this 1/2 times 1, that part's already rational. So if we try throwing that into Q, we're not going to get anything new and interesting. So why don't we just try throwing in the square root of 5? Do we get the same field just by throwing in radical 5 as we do by throwing in 1/2 times 1 plus radical 5? So first, let's think of this metaphor of an extension field being like a vector space over Q once again. So here are the rational numbers. I've listed a few of them, but of course all of the infinitely many non-integers in between are also a part. And then we have a number like square root of 5, which is irrational. So we're going to sketch it in here as though it's kind of orthogonal to the rational numbers. It makes that little right angle there. And if I'm going to include the square root of 5 inside of my extended field, then that means that every multiple of the square root of 5, every rational multiple, must also be included. So it gives me an entire perpendicular axis that I'm going to call the square root of 5 axis. And this two-dimensional vector space that we get in that construction is exactly what we mean by E2, Q adjoin radical 5. It's going to be this thing that looks like the xy plane, with the x-axis being the field of rational numbers, and the y-axis here being the rational multiples of the square root of 5, and every linear combination thereof is going to belong to E2. So what's a basis for this field E2? At least as it's drawn here, the standard basis consists of the rational number 1 and the irrational number radical 5. So we get this kind of xy plane picture of what E2 looks like. But our job is to figure out how is this different than if we had just thrown in gamma, 1/2 times 1 plus radical 5, all together, the whole thing, not just the radical 5 piece. How can we locate gamma inside of E2? Does it belong? Well, sure it does. Right here at the point 1/2 comma 1/2, we get 1/2 times 1 plus 1/2 times radical 5, and that's exactly gamma. So gamma does live inside of E2. But if gamma lives inside of E2, then every rational multiple of gamma must also live inside of E2. And so we get this little gamma axis, if you like. It looks kind of like a diagonal line inside of E2. And the vector space that we get using the basis of 1 and gamma is exactly E1. But this is exactly the same as the question in linear algebra of whether it's the same in the xy plane to use 1, 0, and 0, 1, the standard basis, the purple vectors, as a basis for the xy plane, or whether to use the vectors 1, 0, and 1/2, 1/2, those would be our little green arrows here, as a basis for the xy plane. And it turns out that both are acceptable. In other words, both of those bases determine exactly the same vector space. So we get the same set. Every element we can locate in E1, we can also locate in E2. And so really there's no difference in the structure of these sets. The only difference is in the basis that we've put down on top of those sets. And when we change the basis in linear algebra, we change the coordinates that we use to express each element of E1 and E2. So as an example, let's suppose I take the number 3 minus radical 5, which we can locate as that red dot right there. In the purple basis, in other words the basis on E2, it's fairly simple to see what the coordinates are, 3 and negative 1, because it's 3 times 1 plus negative 1 times radical 5. What are the coordinates of that point in the green basis, the basis of E1, Q adjoin gamma? Well, we can find that as well, as 4 comma negative 2. How do we know that that's true? Because 4 times the first basis vector 1 plus negative 2 times the second basis element gamma gives us exactly 4 times 1 minus 2 times a half plus radical 5 over 2. That's gamma. But then multiply that out. 4 minus 1 minus radical 5, 3 minus radical 5. So the same element belongs to both E1 and to E2. It's just that we use different coordinates to express that membership in E1 and E2. But the important part is that the set itself is still the same. Both of these bases, the green basis and the purple basis, are spanning the same set, which is our simple extension of Q by the golden ratio. So we express that sameness by saying that these two vector spaces are isomorphic. In other words, we could come up with a one-to-one and onto homomorphism, or if you're thinking in vector space terminology, a one-to-one and onto linear transformation, a square invertible matrix, if you like, that converts us from one coordinate basis into the other. But it's one coordinate basis and another coordinate basis on the same set. So we can think of the sets as being the same, as long as we remember that they might have a different coordinate system on them if we choose to adjoin a different element, like gamma versus the square root of 5. So the news is not all that bad. That simple extensions are uniquely defined, but only up to a choice of coordinate basis, only up to a choice of isomorphism.